Okay, so now as we have covered the basic, now we are going to study the algorithms or graph algorithms actually. So the first is the graph traversal methods. You may have know this graph traversal methods. There are basically two main types of graph traversal methods. The first is DFS. Why this line goes like this? Okay, so the first is DFS and the second one is BFS. So first study about DFS. So what is DFS? Like if you have 2, 3, 4. So consider this graph. Now I want to start the DFS from node 1. Okay. So the DFS means moving towards every node. Okay. In a particular order, the order will be first we take one node and explore it completely. So what I am going to do, I am going to go here, then I am going to go here, then I will return back to this node because I have explored this node. There is nothing coming out of it, so I have explored this node. I will come on the second node again, but as I have visited it, so I will not going to print it again. Okay, so I will explore the second node once again. So next I will go here, and as I have explored this too, so I have explored every node. This is just DFS. Okay, simple. Now we study what have been written here. Okay, so before going further, I must tell you one more case in DFS. Like in DFS, if you have considered, I am not numbering it the nodes here yet, but this is the case. Consider these two disconnected graph. Okay, we have studied about connected. That is, if we can go from one node to second node, one node to another node, like we can go from this node to this node. Okay, so these two are connected node, but we cannot go from this node to this node, but this completely is a part of one graph only. This is a disconnected graph, but it is part of one graph only. Okay, so how I'm going to go from here to here, because when we use DFS, so I explored it. Now my computer will say that nothing left to explore now, so I will just print these three only, but these three will be left. That's why we use a visited array. Visited array tells us how many nodes we have traversed. Okay, so I have explored these three nodes, but these three remaining, so my visited will now come directly to the this node. Okay, and this node it will explore then, and as it get explored, now we have completely printed everything. Okay, so this is one of the edge cases where we use, this is a edge case. Okay, visited array will be used. Okay, now let's study about graph traversal methods. DFS, abbreviated as DFS, is a simple algorithm for traversing a graph. Starting from distinguished source vertex, DFS traverse graph depth first. Every time DFS hit a branching point, a vertex with more than one neighbors, DFS will choose one of the unvisited neighbors and visit this neighbor vertex. DFS repeats this process and goes deeper until it reaches a vertex where it cannot go deeper. When this happens, DFS will backtrack and explore another unvisited neighbor, if any. Okay, as I said, it will come back. DFS traversal behavior can be implemented easily with the recursive code below. Our DFS implementation uses help of global vector of integers DFS num to distinguish state of each vertex. For the simplest TFS implementation, now this compared here, compared the implementation. Implementation. Okay. To distinguish between unvisited, we use a constant value unvisited -1, and visited we another use constant visited 1. Calling DFS U, start DFS from a vertex U marked as visited, then DFS recursively visits each unvisited neighbor. Okay, so this is the main DFS code. I'm not going to obviously circle this, but this is the DFS code. This is a global variable initially on value set to unvisited, that is 0. Uh, in general case, we don't write it as DFS num, we write it as visited. Okay. Now void DFS into U. Here U denotes the node. Node. Now DFS U equals to visited. Visited will tell that it is visited, obviously. For int I, int j equals to 0, j less than int adj list. Okay, so adjacency list I have already told you. So what does this denotes here? This is the all nodes connected to this node. So I must write here that this denotes all the nodes connected to you. Okay. Now this is one more node. This is the neighborhood node of U. Okay. So this is adj list uj. If DFS is unvisited, then again traverse it. If it is visited, then we will move to next neighbor. Okay. This is the case. Now this is very easy code. This is, you can say, the simplest algorithm. You must not have faced any difficulty in this yet, but using it somewhere is like difficult. But let's see, with this we can tackle any problem. The time complexity of this DFS implementation depends on the graph structure used. In a graph with V vertex and E edges, DFS runs V plus E and OV squared if the graph is stored as adjacency matrix. On the simple graph figure, this is the sample graph, not simple graph. DFS starts from vertex U with trigger. Okay, U equals to 0. Now we can say it goes here, it goes here, it can also go here, but I consider it going here because we obviously take the smallest. Okay, so this goes here, this goes here, then this goes here, then it has to, this is already visited, so it will visit here. So first it will print this. Now it will come back and check if there is any unvisited. So this complete has been visited. So now this will no longer be the case. Now we will, now in the main we have already written int unvisited. If unvisited, we traverse from 0 to 8 and say if unvisited, then visit that node. So in that code, 7 will first, not 7, first 5 will be considered as unvisited, so now it will visit it. This is just one node, so it will visit it and marked as visited. Now it will move next to 6. Now for 6 it will first go to 7, marked it as visited, then it will come back and see is it explored fully, not yet, so it will go to 8. Okay, so this is the case. This is easy, I guess. You can see that the sequence of visitation depends very much on the order of the neighbors of vertex. That is the sequence. This sequence is also possible. Any sequence is possible. Okay, but at last, what matters is that we visit every node. Okay, I must highlight this. Also notice that one corner of DFSU will only visit on vertex connected to a vertex U. That is why vertices 5, 6, 7, 8. Yes, I told you that these 4 nodes are unvisited. So we will visit it one by one separately. The DFS code shown here is very much similar to the recursive backtracking code shown earlier. Obviously, it is backtracking code. Like we already know this is how backtracking code looks like. This is nothing new. Backtracking automatically unflag and reset by not revisiting vertices of general graph runs in V plus E. But the time complexity of backtracking is exponential. It is not a backtracking code because we are not unmarking the visited. Okay. Now we see one problem associated with this. So this is a problem statement. Let's study it. Vertex X dominates vertex Y if every path from the A start vertex. Okay, so vertex 0 is the starting vertex of this problem. Maybe here is some error. To Y it must go through X. Okay, so vertex X will dominate vertex Y if every path from the starting vertex to Y must go through X. Like if we want to reach 3 and this is the starting, no, if we want to reach 4 and this is the starting vertex, we must visit through third node. Okay, so here this node is the 3 dominating 4. Okay, but we can see that 2 is not dominating 4 because it must not go from 2, it can also go from 1. Okay, as we have options, so here only 3 is dominating 4. If Y is not reachable from the start vertex, then Y does not have any dominator, obviously. If we cannot reach from here to here, then it does not have any dominator. If every vertex reachable from the start vertex dominates itself. For example, in the graph, vertex 3 dominates vertex 4, since all path from 0 to 4 must pass through 3. Vertex 1 does not dominate vertex 3 since there is path 0 to 3 that does not include vertex 1. Our task given directed graph, our task given a directed graph. Okay, so this is a directed graph because we can see here is just it has direction. The problem is about reachability test from determine the dominators of every vertex. So find the dominators of every vertex. This problem is about reachability test from a start vertex, vertex 0. Since the input graph for this problem is very small, we can afford using the backtracking algorithm. Run DFS 0 on the input graph to record vertices that are reachable from 0. We can avoid you to use the following algorithm: V into V square algorithm. Run DFS 0 on input graph and read. Not this is not backtracking. Then to check which vertex are dominated by vertex X, we temporarily turn off the outgoing edges of X and return DFS 0. So how we are going to solve this problem? This is about that only. This problem is about reachability test from vertex start vertex. Since the input of this problem is small, p less than 100, we can afford to use the following algorithm. Run DFS 0 on the input graph to record vertices that are reachable from vertex 0. Then to check which vertices are dominated by vertex X, we temporarily turn off all the outgoing edges of the vertex and return DFS 0. Now a vertex Y is not dominated by vertex X if DFS 0 initially cannot reach vertex Y, or DFS 0 can reach vertex Y even after all outgoing edges of vertex X are temporarily turned off. Vertex Y is dominated by vertex X otherwise. Okay, so this is simple. I repeat this process. And what is the tip? We do not have to physically delete vertex X from the input graph. We can simply add a statement inside our DFS routine to stop traversal if it hits vertex X. Okay, so you must have understood the task. So this is the problem. Okay, so let's discuss the sample input output of this problem. Let's first try to create the adjacency list of this graph. So I guess I can. Yes, I can make a boundary. Okay, yeah. So for node 0, we see it is connected to node 1 and node 2. Node 0, node 2, and then we see node 2 is connected to node 3. Node 3 is also connected to node 4. node 3, then it is connected to node 4. Okay, so now for this graph, if we try to make the adjacency list, it will come as, for 0 node it will come as 1 2. Okay, for second node it will come as, not second but okay, uh, 0 and 3. For okay, no, not 0, because we can see that here it is directed graph. Okay, so as it is directed, 0 will not come, only 3 will come. Okay, first erase this to make this more clear. Yeah, so 1, let me give the direction to, for 1 3 will come, for 2 3 will come, for 3 4 will come. This is the adjacency list for this graph, adjacency list for this graph. Now what we are going to do, how the output is created. This is the sample output. Okay, so this is here the sample output. Now I guess you must not face any difficulty in understanding this problem. Now how it is written here. So 0 node is self-dominator. Some points to be noted. 0 is self-dominator, and 0 also, 0 dominates everyone, including itself. Okay, so this is the first point to be noted. 0 dominates every node, including itself. Also, you must note that you must understand it that every node dominates itself. Like the first node dominates itself, second node dominates itself. Third node dominates itself and also the next node. Okay, this node dominates this node. Okay, dominates itself. So this we also understood, that every node dominates itself, 0 dominates every node. Now how we are going to use DFS in this problem. So first we will start from the 0 node, mark it completely as yes, and yes. Then we will go to the first node and see if the connecting node can be visited by some other nodes too. If it can, then this is true. If it cannot, then this is false. Okay, so we are going to use backtracking in this code. Maybe I want to use backtracking. So first we go here, mark it as yes. Then we go to first node, we go to connected node to this, and mark it as and 1. Okay, currently marking it as visited. Okay, then going to this node, then going to this node. Okay, so these all nodes will be in start marked as yes, but now we will come back, and while coming back we will mark it as unvisited. Okay, we will mark it as unvisited. We come here, we come here, and see, this is visited. Okay, acha, okay, so we cannot come back because this is a directed graph. Okay, so there is no path to come back. So we visited till here. Now we will again start from mm, I guess 0. Mark every node as unvisited. Okay, so we are not currently marking anything as yes. We will go to second node. I guess we should start from second node itself because it is unvisited. Okay, so we go to second node directly without any, without going to the first node, 0th node. So we will go to second node, we will come here, we will come here. So if we see that if one node is visited more than once, then all nodes surrounding to, then that node, then all the prior nodes connected to that node is does not dominate it, does not dominate that node. Okay, so what I mean here is that if, wait, wait a second, let me think on this. Do I have been given any hint here? We do not physically delete vertex x from, we can simply add a statement inside our DFS routine to stop the traversal if it hits vertex x. This problem is about reachability test from the start vertex 0, so the input graph for this problem is very small. Run dfs0 on it to record the vertices that are reachable from vertex 0, then to check which the vertex are dominated by. Turn off on the outgoing edges of the vertex x and rerun dfs0. Now vertex y is not dominated by vertex x if dfs0 initially cannot reach vertex y, or dfs0 can reach vertex y. Okay, so you must have understood this till now. This says that when we go to one node, okay, so understand this, like I went here, so I will turn off on the outgoing, so I will close this path, then I will again go to dfs0 and try to run this. If I can again reach 1 even after turning off on the outgoing path, then simply I can say that this node uh, does not dominate, that 0 does not dominate 1. As we can see that we cannot go 1 without uh, from any other methods, so 1 depends on 0. Okay, from this every node depends on every node. So for 3, if we close on the outgoing edges, okay, and we try to reach it from here, and we say that this path is done, so we will cancel this off. Now if we can again reach 30, then we can simply say that it is possible to reach 3, no node dominates 3. Okay, I can simply say, so we can see that no node dominate 3 itself except itself. From this scenario, obviously 0 dominates, but no other node dominates 3. This is the case. Now for 4, we can see that 3 dominates 4. Okay, that's why this is awesome problem of DFS. Like we'll simply shut down on the outgoing edges from this, and if we can still reach 4, we will shut down the edges. And in a recursion we can use backtracking, so when we come back we again mark it as unvisited, and simple. Okay, but we will not mark it as unvisited because it does not neither visited unvisited case, because I guess we have been given a connected graph only, there must not be not connected graph. Okay, So this is a good problem. We have just discussed the idea. We will solve the problems later. Okay. We are currently just discussing the ideas. So idea for this problem is given here. Let me highlight this. About reachability test from starting vertex. We can afford using the following V into V square algorithm. And read on DFS 0 if vertex Y is not dominated. If it initially cannot reach or can reach vertex Y even after all outgoing edges of the turned off vertex Y is dominated by vertex X otherwise. Repeat this process for all nodes. We do not have to physically delete X. We can simply add a statement inside DFS to stop the traversal if it hits vertex X. Okay. So this is a nice problem. I guess this would have been rated 1900 to 2000 rated on Codeforces. So we are obviously going to solve this, but not right now, later. Now first let's study about another algorithm, which is BFS or breadth first search. So BFS or breadth first search is another graph traversal algorithm. Starting from a distinguished source vertex, BFS will traverse the graph breadth first. So what is breadth first? Let's discuss that with a tree. Not exactly general graph, but particular tree. Okay. So if we study breadth first, this just mean this, then this complete, then this complete. Okay. But how did it came? Like when we print the breadth first, we get this, then this, then this. But how? So by this, first I will print this, then it will visit all nodes connected to it and then print. Then these two nodes will visit all the nodes connected to it and then print this. So every node will visit to every other node connected to it and then print. This is just the breadth first search. Okay. Like in graph, first this will be printed, then this will be printed. Okay. Hope you have understood the BFS. That is, BFS will visit on the direct neighbors of the source vertex, direct neighbors and layers by layers. Okay. BFS starts with an intersection of source vertex into a queue. So how does it start? First let me change the color. I guess I wanted blue now. So yes, BFS will visit the direct neighbors of the source vertex, neighbors of the direct neighbors, second layers, and so on, layer by layer. Okay. So how do we implement the BFS? BFS starts with the insertion, not intersection, insertion of the source vertex into a queue. Then processes the queue as follows: take out the frontmost vertex U from the queue and queue on the visited unvisited neighbors of U. Usually the neighbors are ordered based on their vertex number and mark them as visited. With the help of queue, BFS will visit vertex S. And on the vertices in the connected component that contains S layer by layer BFS algorithm. Acha, okay. So I just read it. I hope you have understood. BFS starts with insertion of source vertex S into Q. First, this will be inserted. Then processes on the queue as follows: take out the frontmost vertex U from the queue and NQ on the unvisited neighbors of U. Then this will come out and it will visit on the unvisited neighbors, okay, and push them into queue. So this will also be pushed into queue, this will also, this will also, and this will also, and mark them as visited. So this node will be marked as visited, okay. Usually the neighbors are ordered based on their vertex number. With the help of queue, BFS will visit every vertex, will visit vertex X, vertex S, and vertices connected component that contains S layer by layer, okay. BFS algorithm also runs in OV plus E and OV square, just like DFS. On graph, using an adjacency list, okay, if graph is represented as adjacency list, then it will run in OV plus C. If it is, so let me write down here with a pencil. Pencil is not good. Okay, so if graph is represented as list, then OV plus E. If graph is represented as matrix, then OV. Okay, this is the case. Implementing a BFS is easy if you utilize C++ STN or Java API. We use queue to order a sequence of the VI visited, if it has been visited or not, which is at the same time record the distance of each vertex from the source vertex. The distance computation feature is later used to solve a special case of single source shortest path problems. So this we will study later. I write later. So now what we need: one queue, two visited array. Okay, so we see three node recursion. We see node recursion has been used here because we are using directly queue. So we directly can start from the int main. First visited array, all visited has been marked as 0 initially, or no, this is the, we are also finding the distance using this visited array. So we first initialize shortest distance. We first initialize it with infinity and mark the starting node. S is the starting node. Start node. Okay, so that is marked as 0. Then we use the queue and we push back S in it. And why not queue is empty? Because we first take out, we currently have this first node in the queue only, S. As it is not empty, it will go in this loop. This is the first node. We take it out on, we store that node in the someplace as U, then we pop it, we remove it. Now we will visit every node connected to this. So for this the same. This is its neighbor. If dv dot first is infinity, then we will simply mark du plus 1. Okay, so the distance to parent node plus 1. Distance of parent node plus 1. This is the thing. Okay, so I guess it is easy now. So this is the code. It is easy, and we also mark the. We also got to know the distance from that, or we can say the height in trees. So in trees, this is known as height. Okay. Now you can see that we have written just this and not as dv dot first equals to min d dot first. We could have also written that, but we must know that only the first time when any node visit that node is the shortest, because we are moving layer by layer. So after the first iteration, whatever layer will come, it will always be greater than this distance. Okay, that's why I have written just this if div first equals to infinity. Now what is this? This is just an example iteration. Okay, if we run BFS from vertex 5 source on the count connected undirected graphs on below, we will visit on the vertices in the following order: layer 0 visit 5. This is just the animation. Okay, so for 1 it will visit 5. This is layer 2, this is layer 3 plus layer 4. Okay, you may have understood this. To show that either DFS BFS can be used to visit on vertices that are reachable from the source vertex. Solve this using dominator using BFS instead. The same dominator problem that we'll solve later, we can also solve by BFS. Why do DFS and BFS run in OV plus E if the graph is stored in adjacency list, and becomes slower run in OV square if the graph is stored? These are the just for understanding. Finding connected components. This is one of the most important topics. Like I recently have seen a problem with this, and as I have not studied the graph at that time, I could not solve, but later I found out that this is a topic of connected components. Then I thought that if I would have studied graph at that time, I would have solved the problem, but no worries. DFS and BFS are not only useful for traversing graph, We use highlight. DFS and BFS are not only useful for traversing graph. They can also be used to solve many other graph problems. The first few problems can be solved with either DFS or BFS, although some of the last few problems require are more suitable for DFS only. The fact that one single cone of DFSU or BFSU will only visit vertices that are connected to U and can be utilized to found a number of the connected components in there. We can simply use the following code to restart DFS or BFS from one of the unvisited vertices and find the next connected component. Okay. The fact that one single cone of DFS or BFS will only visit vertices that are actually connected to you. Okay. The first cone of DFSU or BFSU will only get the connected components to you. Can be utilized to found a number of connected components in an undirected graph. We can simply use the following code to restart DFS and BFS from one of the remaining unvisited vertices to find the next connected component. Like I told you earlier, this and this are part of one graph only but disconnected. So if we start from here and goes like this and we restart the DFS from this node, we can go like this. Okay. Inside this is a DFS solution. Number of connected components, assign unvisited, print I if DFS name is unvisited, print start the DFS from that node only. For the sample graph, okay, that the graph above figure 4.1, oh, above that only. Okay, so this is not, this is useful for finding connected component. Labeling, coloring the connected components. DFS or BFS can be used for other purposes than just finding and counting the number of connected components. Here we show how simple tweak of OV plus E DFSU can also use BFS, can be label, used to label, also known as CM terminology, to color and count the size of each component. This variant is more famously known as flood fill and usually performed on implicit graphs, usually 2D grids. This is a trick to explode an implicit 2D grid. South, southeast, east, northeast, northwest, southwest neighbors. So in 2D graph, we can go from here, 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 here. In some problem require this. According to our need, we can select the coordinates. Okay, this is the row coordinates, this is the column coordinates. Like what is this? 1 0, 1 0 is nothing but going down in the same. 1 1, this 0 1, like this. Okay, so we are moving in that one. Now flood fill or labeling or coloring the connected components. If r equals to 0, r greater than, if we return to one of the borders, if we reach to one of the borders, okay, these are the borders. If we reach to any of these borders, then we will simply return 0, that it is outside the grid, not borders. What I have done here, if we reach, this is a adjacency matrix, okay, and we are simply moving, like I give you an example, myself getting confused after writing this. So why not I understand, this is a grid we have been given, okay. Now it may be possible that there are few dots here which are connected, there are few dots here which are connected. Now we have been asked, can we move from this dot to this dot by moving in these directions, okay. So if we go behind this, more than this, less than this, behind this, and more than this, outside, for every outside case we will return simply 0, that we cannot reach from this node to this node, okay. We cannot, we could never, we can never, okay. So in a grid, in grid problems, we can see that these are not of one category, and that's why we are coloring it. So these are not colored one, okay. I'm changing the color, I guess we should have make it better. So these are connected components and these are colored one time. Now we still see that there are remaining some. So if it is not in this, then we are coloring it other color. Like let me choose one more. So this all unconnected components are colored differently. Now we again see that these are the same things, so we are going to color it. Now for the remaining, we still see that this and this are not colored. So whatever is connected, we have colored it to this, and whatever is not, this may be helpful to some problems, okay. This variant is famously known as flood fill, and usually performed on implicit graphs where both are present. What does it mean by implicit? Where connected and unconnected components or no components are all present, okay, or mix of graphs. For grid problems it is mainly used, okay. So when we talk about graph, we don't know about what type of problem come in graph, okay. So I may have something I can show you that will tell you the types of graph problems, okay.